Yes.
It doesn't say on the syllabus. It's upstairs.
Well, if we're in good shape with everything, we can just meet upstairs. No questions about mass spec? Okay. Yes, we'll meet upstairs. Okay, pick up where we left off at with substitution reactions. Substitution reactions. We looked at the transition state for the SN2. Concerted backside attack leads to inversion. Attack goes through a planar transition state, which is sp2-like with the p orbital. And then as the leaving group departs, the groups actually come the other way, and you lead to inversion, like an umbrella inverting in the wind. All from a result of backside attack. We did backside attack 6 weeks ago, 4 or 5 weeks ago. We looked at it a little closer now. The idea of inversion, backside attack. Okay, the transition state. Understanding the transition state can help us predict reactivities. Both of these reactions are known to be SN2. I minus replacing Br leaving group. Reaction up here is much faster. This is much slower. Why is this slower? Anybody? Why is the reaction below slower with the leaving group on the cyclopropyl ring there? Heard this. What was this? Well, what about the ring string? What about the bond angles?
It's a small constraint bond angle, and in order for the transition state has to be 120 for the bond angle.
In the transition state, the angle between the three groups becomes what?
120.
The three groups, other than the leading group or the new group, the three groups have bond angles of 109.5 if the carbon's tetrahedral. But in the transition state, that angle becomes larger. It becomes 120, sp2-like. Okay? These two carbons here, this bond angle, can it become 120? No, it's 60 degrees right here. It's going to have a very hard time becoming 120. This is much closer to the ideal. In the transition state, the groups spread apart. We're going to have a tough time spreading apart here. Does it have to be 120? No, that's the ideal. Just like, does tetrahedral have to be 109.5? No, many are less than 109.5. But the ideal is expanded upon where it starts from. This ring is going to have a hard time expanding beyond where it's starting from. Ninth grade geometry tells us that. You guys take ninth grade geometry? Good. So we can explain this and not just let it be some mystical thing here. Make sense? Okay, at this point we're going to look at different topics. Of course, the handout labels the topics. And for a while now, we're going to kind of focus on SN2. Okay? The next topic is reactivity of various electrophiles in the SN2 reaction. What's the electrophile? Well, it's the thing that reacts with the nucleophile. Nucleophile loves the nucleus. Nucleus is positive, so the nucleophile loves positive. Either a positive charge or partial positive. What does the electrophile love? Electrons. It's the thing that gets attacked by the nucleophile. The lone pair attacks the electrophile. Okay, the electrophile contains the leaving group. Okay? Back over here on our mechanisms. Here we formed a carbocation, right? And the nucleophile attacked the carbocation because minus likes plus. Down here, I'm not sure if we said it. I don't think we did. Why would hydroxide attack this carbon in SN2? I'm sorry, it's below here. I thought that was the first one. The second one. The second was SN2. Did we form carbocation? No. Then why would the nucleophile attack that carbon? If it wasn't a carbocation. Down here, right? Why would this attack this carbon? Because it is partial plus. Yes, there is a dipole here. Okay? It's not a full carbocation, but it's a partial plus from polarity. And since it's partial plus, it's going to like the electrons. Or you can say the electrons are going to like it. But they like each other, and so this is said to like the electrons. So this is called the electrophile. But it's partial plus. Now, while we're talking about this, physics, you guys take physics? It's an important course. That's why it's part of your curriculum. What is it meant to teach you? You should think about that. Is this going to react faster with a carbocation, or with, which is a full formal plus, or a partial plus? Which would it react faster with? Full positive, right? So if we only have partial positive, is this going to be a easy reaction, or will it tend to be more difficult? Relatively. More difficult compared to if it was full positive, that should be, okay, yeah, SN2 tends to be a little more difficult because of that reason. SN2 often requires a little heat to get it to go, to force the nucleophile to get there and do something. Okay. So, reactivity of various electrophiles. Things with the leaving group. 1. Effect of a p orbital being immediately adjacent to the reaction site. If you look at the leaving group here, okay, nucleophile attacks here, kicks off leaving group. Adjacent to that, immediately adjacent to the reaction site, p orbital, right? There's a p orbital here, yeah? Attack here, p orbital next door. Everybody agree? Attack here, p orbital next door. Everybody agree? Attack here, p orbital next door. Actually, 2 next door there. Only need 1. What does this do when you have a p orbital adjacent to the reaction site? It makes it more reactive. These are all more reactive in SN2 than, for example, this. Attack here. Is there a p orbital adjacent to the reaction site? No. Less reactive. Why is it more reactive if you have a p orbital adjacent to the reaction site? Let's go to the transition state. Because that's where the activation energy is at, right? In the transition state, you had it drawn there, but what did we have between the hydroxide and the carbon as the bond was being whatever? What was it, bromine or chlorine? Didn't this look like a p orbital? Okay? And if you have next door to that, that's where the reaction is taking place. If you have a p orbital next door, what are you going to get? between the two p orbitals? You're going to get overlap. In the transition state, you have p orbital overlap. What does that do to the transition state energy? It lowers it, stabilizes the transition state. And if you stabilize the transition state by this p orbital overlap, it'll make the reaction faster. Okay? Didn't we say the transition state had sp2-like character with the p orbital here-like? These electrons, as they're being breaking and stuff, they're interacting with the next door. Okay? And yes, you could spend a whole weekend thinking about this and the physical nature of this. But if you just accept that it's p orbital overlap and that's going to be a stabilizing thing at the introductory level, then we understand why all these are much more reactive than something like this. In fact, all of these up here are so reactive they are toxic. Because your body has lots of nucleophiles, like amino groups in your DNA or your proteins. Okay? And you are exposed to one of these, you're going to start reacting with the proteins in the eyes very easily. This, not so toxic, because the reaction doesn't take its place as readily. Now, you don't want to be drinking that here. But it's not as toxic as these up here. It's not as reactive. In fact, everybody ever heard of ethyl chloride? Play baseball, ever heard of ethyl chloride? Watch baseball? Ever watch a baseball player, they foul a baseball off their ankle, and it hits the ankle, and they're like, No? You guys don't want, okay, yes, thank you. Okay, the trainer comes out, what does the trainer do? Spray something on it. What is the trainer spraying on it? Yes, ethyl chloride. What does it do? By the way, this is also used in like dentistry offices.
Is this like the cold, like it evaporates immediately almost? Real cold?
It numbs the area because it's a compressed gas. But the gas, as it evaporates, it takes heat to evaporate, and if you remove heat from the surroundings, you're going to become cold. It makes the area cold. Okay? Numbing, also used, like I said, in some medical practices to numb an area. Maybe for like a dermatological procedure. Okay? It's ethyl chloride. Now, I remember 20 years ago, Tim McCarver, if everybody knew it, baseball announcer, he said, here he comes, he's going to spray ethyl chloride on him. Called it ethyl chloride. Okay? I would call it ethyl chloride. Yes. It's got a carbon with a leaving group. It's not that toxic. Nobody would ever spray one of these at the ball field because you'd have to evacuate the ball field. It'd be like tear gas or something. Reacting with the proteins in the eyes, okay? Much more reactive. Okay, 2. Effective carbon substitution at the site of attack, or the reaction site. Carbon substitution. Look at this trend. Methyl bromide is much more reactive than propyl bromide. That's more reactive than isopropyl bromide. Way more reactive than this. What's the difference? This is condensed, but if we draw it out, this carbon has nothing but H's on it. Right? Where the extreme is, this carbon has other carbons. And by the way, these carbons have H's. Don't forget that, right? Right? And the nucleophile comes in here, and it's like, boop. Okay, we're doing SN2, right? Yes, that's what the heading said. Okay, concerted backside attack. But the nucleophile over here comes in, and it's like, hold on. Boop, I finally made it in. Well, actually, it hardly never makes it in. And another reaction takes place. This is called steric crowding. Sterics. Okay? There's no sterics here. Because the H's, what are the H's? Well, how big are they? They're really like about that big compared to the carbon, yeah? Okay? Lots of space. Okay, over here. One of the atoms is another carbon, and that's bigger, and it starts blocking it. And what do we call this? This is called a primary alkyl bromide, because the carbon is primary. Secondary, 2 carbons. Tertiary. Okay? This is not even primary. We call this just methyl or parent. Okay? Sterics. Here we go. Sterics is very bad for SN2. This is said to be very sterically crowded. Very bad. And in fact, you never do SN2 with a tertiary halide. It's too sterically crowded. Does it say that somewhere? Any exclamation points?
Yes.
Okay. Sterics negatively affects the rate of an SN2 reaction. In fact, methyl bromide tends to be a little toxic because it's so unhindered. There's no sterics, it reacts pretty quickly. Now there's no p orbital next door, it doesn't even have an atom next door. So it's a different reason for it being so reactive. In fact, this is a gas, and that is actually used to fumigate large buildings like warehouses. Okay? Huge buildings, they just come in and this gas, and then the vermins and roaches or whatever inhale it, and that's it. All the proteins start reacting, and it's going to be problematic. Fair react. You don't want to breathe this stuff, okay? And this is a liquid. It's not quite as toxic. Probably still maybe a little toxic. And then it gets less reactive, and then this is, you know. Okay. Sterics negatively affects SN2. Note, the trend is just the opposite for SN1. What's the rate determining step of SN1? Forming carbocation. Which one's going to make the best carbocation? The tertiary, right? And thus, tertiary halides react faster in SN1. They're the fastest reacting in SN1. Right? So you knew that already. The trend is just the opposite for SN1, but it involves making carbocation. So in this example, I kept the leaving group the same. Okay? We're not looking at the leaving group here. We're looking at the substitution at the carbon site where the reaction is taking place. That's just a little table that is very common from the web. You can see the rate. Okay. As the substitution increases, you see the rate gets slower, negligible, or never. Never. Okay, for us, just never. Tertiary halide. Okay, while we're on the topic of sterics, steric hindrance, crowding can affect the rate of other reactions. Okay? In Organic 2, we cover reactions of carbonyls, like esters or ketones. Sterics there can affect the rate of reacting with the carbonyl. For those who want to look at an effective sterics application in dentistry is with local anesthetics used in dentistry. Some of them are short-acting that will last for 10 minutes, do a quick procedure. And you don't want your patient to be numb all day. Others will last long because you got to do a long procedure and you want to give one shot and let it last maybe all day because it's an all-day procedure. Anesthetics last until the body degrades them by a reaction, metabolism. More sterics, the slower the metabolism, the slower the reaction to degrade them. More sterics, the longer the anesthetic lasts. If you look at some of these anesthetics, okay, like these on Wikipedia, you can do just a search for local anesthetics and find a whole list of them. And look at the structures, you'll see more and more crowding around the carbonyl. Okay? And it's pretty much in line with length of duration. Lidocaine is a quicker acting, and titocaine is longer acting. It's got more sterics around the carbonyl. All right? Sterics is a common thing in organic chemistry and to affect reactivity. Steric crowding. Okay, F. Let's look at leaving groups. We mentioned this on page 1. Leaving groups for your halogens, iodine's the best, then bromine, then chlorine. Actually, fluorine is sort of pretty bad. There's kind of like, fluorine is typically not a leaving group for these reactions. All right. For example, you take this alkyl iodide, react it with potassium methoxide. Okay, of course we know that this is K+, that's O-. Right? And this nucleophile will attack here and kick off the iodide. But it will not kick off the fluoride. Very difficult to nearly impossible to do this. Thus we say that the fluoride is not as good leaving group. It doesn't want to leave. Right? Yes, that's it. So this is your trend. What's the most common leaving group? Probably bromine. Why? You would say, well, why not use iodine the best? Iodine compounds tend to be a little bit unstable. Thus, they're more expensive because they're harder to store. Okay? So bromine compounds are more stable. But bromine's a better leaving group than chlorine. So that's why bromine tends to be sort of the most common. Now, on industry scale, they use chlorine more, even though it's the worst of the leaving groups. You ignore fluorine. Because chlorine tends to be cheaper. And so they go with a cheaper leaving group, even though it's not as good of a leaving group. For research scale, bromine's the best. At the best. Okay. Let me ask you this, a little bit counterintuitive. Which compound has more partial plus on the carbon? Which it's meant to be the same size. Which compound has more partial plus, top or bottom? Bottom, because fluorine's more electronegative. So it sounds like, shouldn't this be more reactive then? I mean, shouldn't the O- be more attractive here? Yeah, perhaps. So that's why it might be a little counterintuitive. But let's ask this. Now this should be all right. We're making I- here. Over here we're making F-. Right? I mean, that's I-, that's F-. Which one of these is more stable? I- is more stable. So that kind of makes sense. I is more willing to leave because it becomes a more stable thing than what F would become. So there's different things here that kind of conflict. What we do know is if you go to the lab, this is easier and this is hard. So we have to go with that this is being, that's sort of a conflict there that doesn't make a lot of sense. And we say, well, this is the reason we're going to advocate for. This explains the observations. where this doesn't really explain the observation. Another thing you can look at for what explains this is if you look at bond strengths, the CF bond is stronger than the CI bond. So that makes sense. It's easier to break the CI bond because the CI bond's weaker. So you can find the right arguments to support your experimental evidence. Okay, what was that? Halogens. Okay, your halogens are good to go, except for fluorine. What about other atoms? What about oxygen? Is oxygen a good leaving group? Well, let's look at an example. What if you take, instead of a halogen, hydroxyl, and we have the same nucleophile, and we might say, I'm going to come in here and attack and kick off the hydroxyl. This is now bonding to the carbon, and we kicked off hydroxyl and made KOH. Well, that would not work. No. No reaction. So what does that tell you about the ability of OH to be a leaving group? No good. Bad leaving group. Not a leaving group. OH is not a leaving group. OH will not act as a leaving group in a slow rate determining step. Why did I not just say that? OH will not act as a leaving group. Because it will act as a leaving group if it leaves in the fast step. Because if it leaves in the fast step, leaving group ability is not as important. If it's leaving in the rate determining step, the leaving group ability is more important. You agree? Okay. And which mechanism does the leaving group leave in the rate determining step? SN1 or SN2? And which mechanism of the two we're looking at does the leaving group leave in the rate determining step? Brian? Anybody? Trick question. Yes, both of them, right? Yes, both of them. Thank you. You know your mechanisms, right? You know the rate determining step, you know them inside out. Yeah, the leaving group leaves in the rate determining step in both of them. Okay? In organic 2, though, we'll see mechanisms that the leaving group leaves in the fast step. The leaving group leaves in the fast step, it's not as important. And hydroxide will leave in a fast step. But it will not leave in a slow rate determining step. Because that's a more difficult step. That's why it's rate determining. On the other hand, if we do this reaction, the alcohol, we can get a product. Because while hydroxide is not a good leaving group on its own, you can make hydroxyl a good leaving group by reacting it with acid, proton, protonating the hydroxyl group. And that's what's going on down here. If we first protonate the group with an acid-base reaction, sometimes acid, what does that give? Boom, boom, boom. Oxygen with 2 bonds to H. This is called protonating the oxygen. Yeah? H plus is called proton. Acid-base reaction. Now this is a good leaving group. Now we can get a nucleophile. These electrons will come in here and kick that off. Up here, if we kick that off, hydroxide Hydroxide, not a good leaving group. If you kick this off, it's not hydroxide. What is it? Just water. H2O. This is going to give, what does this give? It doesn't give the product yet. What does this give? The oxygen now bonded to this carbon, but this oxygen has a methyl and an H. One lone pair left, it's a positive charge. We just made that bond right there. The methanol is now bonded to the carbon. And what left? What was the leaving group? Water, not hydroxide. What do we need to do to get from here to the product? We have to lose the H. What can take the H? Water could. There's got to be a minus here. Okay, it's the same old story we've already. What type of acid might you use to protonate the OH? Strong acid. Okay, strong acid. Such as sulfuric, and we have HSO4 minus. Yeah. These electrons take the H. These electrons stay behind. We did steps like this when we hydrated alkenes. Yeah. What does this give? Gives product, and what do we reform? Well, we already formed our water with the leaving group left. We made H2S, H2SO4 reform. So the strong acid is our catalyst. Yeah? OH is not a good leaving group. How do you make OH a better leaving group? Protonated. Protonated with what? Strong acid. The strong acid serves as the catalyst. It makes the leaving group better. Now the reaction will take place. Okay? This seems relevant to the lab we're doing this week, yeah? Question here, I think, on the next page. Up here, the nucleophile was shown to be methoxide, the anion. I think we can look at the next page. Top. Why would that top reaction not work? What if we try to do that like that? I mean, we got H+, we can protonate this, and then our nucleophile can come in and kick off the water, right? Can we envision a reaction with these components? Why would it not work though? This reaction is not going to work because these two will react with each other. Methoxide is just like hydroxide, just got a methyl group on it. It's going to react with the acid. You can't have your cake and eat it too. You can't have acid and base in the same reaction. If you put them in there, you can't say, okay, acid, I want you to react with the alcohol, protonate it. Don't react with the methoxide. It ain't going to listen to you. It's going to, and acid-base reactions are immediate. It's just going to quench. You no longer have the acid. Or if you have enough acid, then you're no longer going to have the base. What did we use in the previous example? We didn't use methoxide. We used the neutral version of the nucleophile, methanol. Can methanol be a nucleophile? Yes. We didn't use the anion. We used the neutral. Now, common mistake is some of you guys are going to try to deprotonate and form the anion here. No. We're under acidic conditions. You're not going to form anions like that under acidic conditions. Everybody agree? This is like just like hydroxide. Right? There's no difference in those in terms of basicity. Very slightly. This is slightly basic because this donates a little bit. Maybe slightly more basic. They're both anions. Under these conditions, are you going to start generating hydroxide? No, that doesn't make sense. So it also makes no sense to start trying to generate this. Neutral nucleophile will react. Now, would that be more reactive? Is there a partial plus here? Yeah, I mean, because once that becomes positive, it's pulling even without positive, partial plus. This will react faster. But again, you don't have that. You can't have that. You're using the weaker nucleophile. But you can do this. It probably is going to require heat. Because you've got a pretty weak nucleophile. We'll talk more about nucleophiles. Okay. Now, reaction is very common here for alcohols. We're looking at alcohols, is to react them with HX, where X being halogen. Very common reaction. Also seems relevant to the lab we're doing this week, yeah? Is this a good leaving group? How do you make it a better leaving group? Protonated with what? Strong acid, H+. Do we have H+ in this reaction?
Yes.
HI is a strong acid. It supplies H+. Okay. And so we can protonate, yeah? Boom, boom, boom. Oxygen becomes protonated. By the way, this is an acid-base reaction. This is an equilibrium, right? Which side's favored, top or bottom? Plus what? I minus? I don't know which side's favorite. I have to think about it. But here's the point. Just because I'm doing it doesn't mean this is favored at equilibrium. Maybe it's a very bad equilibrium and only 1 out of a gazillion is protonated. Well, guess what? That 1 out of a gazillion then reacts again. Let's do a reaction again. What can take place here? This can be a nucleophile, and we can come in here and kick off the leaving group, and what does that do? There you go. There are your products, right? And what mechanism did we just do here? SN2. Okay? And somebody's going to ask, but I thought SN2 was only 1 step. How many steps is an SN2 reaction? How many steps for SN2? 1? But I did 2 steps here. That's a step. I thought SN2 did not contain an intermediate. I thought it was concerted backside attack. Is this an intermediate? Yes. That is, this is not part of the SN2. This is an activation step, or activating LG, okay? That has nothing to do with the substitution step. When we do the substitution, this is being substituted by the iodine. How many steps in going from here to product? 1. SN2. It's just, there's no intermediate. Okay? So don't confuse that. But I have students all the time say, I thought SN2 was 1 step. And this is 2. First step is an activation step to make the leaving group better. Then you do the 1-step substitution. Okay. So, a very common reaction is for alcohols is to convert them to alkyl halides by reaction with HX. Where the HX applies the acid and the nucleophile. Make sense, yeah? Now let me ask you, could we substitute this with, instead of this, could we have used sodium iodide and H2SO4? Could we have used those two things instead to accomplish this reaction? What do we need to accomplish this reaction? We need H plus to make the leaving group better. Does that over there supply H plus?
Yes.
We need I minus to act as a nucleophile, because that's what we want to replace the water with. Does that over there supply the I minus?
Yes.
Yes. You can do the same reaction with that over there. And this is where I can comment on memorization. If you memorize HI gives this, then you see this, and you have no idea what that is. But if you understand the components of the reaction and what's needed to accomplish the reaction, then you say, yeah, it's over there too. So you think like that. Right? Because HI is actually very uncommon and unstable. In the lab, these two are more common, and it may actually be done like that over there. In textbook, though, we can use HI. Okay. What have we done up here? We made OH a better leaving group. I would broaden that out. We really made the oxygen a better leaving group. Doesn't have to be an OH. Down here, you propose a reaction down here. When I say propose a reaction, that is, it's not something we memorize. We assess what's going on, what type of reactivity we can have, and then we propose a product. How do you make oxygen a better leaving group? We can also expand that out. Protonating it is one way. Really, what do we make the oxygen up there? We turn the neutral oxygen into a positive oxygen. The most common way to do that is to protonate it. There may be other ways to make an oxygen positive. Does it have to be an OH? No. It could be really, okay. Can anybody propose a product down here? And actually, let's probably look at that first thing on Friday, okay? Let's see what we're looking at, okay? Because we need to probably discuss that answer a little bit. See what you get there. What type of product can you propose? We are doing substitution chemistry. That's the name of this handout. Yeah.
If you protonate that oxygen, couldn't it just shear off and the cation be resonance stabilized so it would be racemic?
Draw that out. Let's look at it. I want to see the cat. I think you want to see it too. Because if you look at it, you may find a problem.
Okay.
Very common. Questions. But as soon as you draw it out and look at it, then it becomes more clear. All right? You got problems, okay? And once you start drawing stuff, then your answer becomes obvious. That's why when you come ask me a question, I'd be like, go work the problem. Then you'll find your own answer. All right? You don't need me to tell you your answer. Okay. Let's see. We're about out of time, but what was A? A was making, protonating the oxygen, essentially, making the oxygen positive. What's another way to make OH a better leaving group? Convert it to a tosylate. Okay? On the alkene handout, the diene handout, the back, there was this synthesis of Tamiflu, Gills Alder. We also had a mesylate. Take a look at that. We'll look at that next time. Tosylate, mesylate, things like that. Back this week, upstairs, yeah, we'll get going at 2:30. Shaken, not stirred. Converting an alcohol to an alkyl halide. Okay. Have a good day, guys.